Welcome to Lecture 16 of Computer Systems 214. Today we'll be looking at sequential logic. So we'll be taking it away from combinational logic and we'll be looking at new devices, and specifically we'll be looking at latches and flip-flops. Now this lecture is made up of a few things. The first thing is we'll be looking at the definition of a bistable device, which is needed to define the remainder of the lecture. And then we'll be taking it very slow. Now I want to tell you where we're heading so that you understand the path that we're taking. We're heading to a point where we have a single device that can store a single bit in a piece of memory, and that memory is activated by a triggering edge of a clock. So that's where we're working towards. That device is called a flip-flop. In New Zealand they call it a jangle. Now the way to get there is we have to go through working into latches, looking at latches, and latches are electronic devices that latch onto either a 1 or a 0. And we'll be looking at SR latches, so we're starting from scratch, then into a gated SR latch, a gated D latch, and then we'll take that further into where we look at a D flip-flop. Right, just in terms of where we're at the moment, we're still looking at logic and digital circuits, and we're working our way up to get to the microarchitecture and the architecture and then the operating system. So that's more or less the context of what we're looking at. So let's start off. When we started, we looked at combinational logic. Now you'll remember for combinational logic, we said it does not have memory. Combinational logic is just a combination of AND gates and OR gates, and we had one very specific definition that formed part of the bigger definition of combinational circuits. It was that there can't be a feedback from the outside back into an input of any of the combinational circuit sub-circuitry. So there can't be a mechanism by which the output is used as an input somewhere in the circuit. It must be a nice single directional flow of information. Now we're going to introduce feedback, and what happens with feedback is that you have a memory effect. The output doesn't only depend on the current input, it also depends on all previous inputs. So it depends on what sequence of inputs were applied since power on to get it to where it is today. A very nice example of memory is your body. So if I get a cut, I have a scar, that is memory effect that's built into my body. It can remember that. Or I am the result of all the meals that I've had since I was born. Same type of thing. It's just for now, we're going to provide that feedback mechanism from the output of a combinational circuit back into its input, which basically takes it away from being a combinational circuit and turns it into a sequential circuit, something that contains memory. Okay, so hopefully that makes sense, but we'll do quite a few examples, so it should make sense in the next few slides. So the first thing I want to introduce here is the bistable element. This definition is about a device that has two, that's what bi means, two stable states. So it's either high or low. And as you can see, we've introduced a feedback mechanism here where the output drives back into the input. And on the left-hand side and the right-hand side, we have two circuits. They're exactly the same. So on this side, it's just drawn as a nice little feedback loop. And for this one, we've just moved them about. So let's quickly analyze this. If this value is 0, then this is 0. So this is all low, 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 low. This goes through an inverter. So this will be high. It will be a 1. And then this inverts it, so it turns into a low again, into a 0. So it is self-reinforcing. That's what it's doing. It has the circular effect where the output perpetuates back into the input and perpetuates itself to be the same value. So it latches onto a low. If, however, this was high, this is high, this is high, this is high, it inverts, this is low or a 0, and then this turns into a high again. So it self-enforces a high or a low, depending on which states it's in. Now, typically, we don't use a Y or an X for the output. We typically have an output Q here that we indicate. And The idea here is that that is the normal output Q, this is the inverse of the output Q, and this is not very useful. So the issue is, even though this is easy to analyze, and even though we've made something that stores a single bit, the question is, so what? It can't change. We don't have a mechanism to bump it to go into a 0 state and then stay there, or bump it to go to a 1 state and stay there. It's just a stationary, or at least a passive, that's it. It's like a passive state. It can't change, it doesn't change. So the question then becomes, how can we change its state? How can we change it to not be stable in 1 or 0, but then change it by adding an input that forces it into one of those two states, and then it can stay there. So that's what we're working towards now. The reason we need this is these type of circuits are everywhere. Everywhere in the real world, when you want to control something like an engine controller or like an alarm system, that's the example that we have on the slide there, you need some form of memory. So let's just consider this as an example, just to convince you that it's worthwhile doing. In this setup, we have an alarm system where there's a sensor, and as soon as this sensor triggers, it says something's been detected, the alarm system is supposed to start yelling. It's supposed to start making a noise. Now, as soon as it does so, it must stay in that state of making noise. So we have here a memory element. This will say no alarm, no alarm, no alarm, and then as soon as there's a trigger, it'll say alarm, and then it'll keep saying alarm, 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 until we reset it. Now, in order to do that, we need a memory element. We need something to remember the state of being in alarmness, its alarmed state. And then only when the reset is pressed does this memory clear, and then it remembers its state of not being in an alarmed state. So this is really a very powerful thing to do, and it's something that you as electronic engineers specifically will do quite a bit, or control engineers. Okay, so the first device that we're introducing, you need to understand this to build up onto getting to a D flip-flop. So it's very important that you get this. So the basic element is the SR latch. So instead of having two inverters now, we have two NOR gates. As you can see, an OR gate with an inverter at the end, that's a NOR gate. And now we have two inputs. So we have a set input, the S, and we have an R reset input. You can imagine what they mean. The set will turn Q into 1, and the reset will turn Q into 0. And the way that this works is that when reset is 0 and set is 0, it basically just stays in its current stable state. If it was a 1, it keeps a 1. If it was a 0, it keeps a 0. Then, when we make reset 1, and I'm going to rephrase this carefully, as soon as we make reset 1, the value is forced to be 0, and it continues to be forced to be 0 while reset is equal to 1. As soon as we then replace reset with a 0, we take it away again, then this just maintains its state. So while the level of reset is high, I'm choosing the words very carefully, while the level of reset is high, this will be forced to 0. Conversely, while the level of set is high, this will be forced to be 1. So while it's 0, it just maintains its state. So let's say, well, both of those are zeros, it just maintains its state. As soon as set goes high, and while set is high, Q is forced to be 1. As soon as set goes 0, Q just maintains its state, which will then be a 1, I guess, after the set was set, and then it acts as a memory element. So we've discussed the 0, 0 condition. We've discussed the 0, 1 or 1, 0 condition and the 0, 1 condition. The other condition is the 1, 1 condition. But for that condition, it's not really something you want to do. You don't want to set and reset the device. Okay, so not going to happen. I'll talk to you that state in a second, but try not to think about it. Okay, so let's just analyze this real quick. If we have, let's say we have a 0 state here. I'm going to do this in a different color actually. Let's say we have a 0 here. That 0 is fed through all the way here, and I'm going to assume a 0 as well on set and reset. So this 0 goes all the way here. Because that is 0, that is 0. I have a 0 here. The OR gives me a 0, but the invert changes that into a 1. So I can see this is 1. Because that is 1, the 1 feeds back here. 1, or with anything, it doesn't matter what, gives me a 1. The inverse of that is just a 0. So it's self-reinforcing. Let's just check what happens when we then, in this condition, we set the S bit equal to 1 and the reset equal to 0. As soon as we set the 1 here, the output of this OR gate will be 1, which means the output of the NOR gate will change into a 0. As soon as this changes into a 0, you can see 0, 0, 0, 0, 0. A 0 ORed with a 0 gives you a 0. Inverted gives you a 1. So immediately this changes into a 1. Now let's just take it one step further. This 1 then, let's just check if it reinforces. This is 1, 1, and actually let's keep this 1 for the moment. The output there is 1, the output is 0, and we've just seen that takes it back there. So this maintains its state. Let's now change this to a 0 while we're in that state. What happens now? Well, as you can see, the output here, which is 1, is still going to reinforce this 1, which will reinforce this 0, which will push it back here. So this whole thing reinforces itself. And just to reiterate what it does, it maintains whatever its state is as long as R and S are 0. As soon as R goes to 1, and while R is equal to 1, it will force the output to 0, and this one to 1. And then, let's go back to the state where they're both 0. When it goes back to 0, it maintains that 1. When set, it changes to 1, and while it's equal to 1, it's like while its level is equal to 1, this will be forced to a 1, and then when set goes back to 0, it maintains that 1 until the reset is set. So now we have a nice device. We have a set reset latch which can remember values, and the values that it can remember we can control. So we can say remember a 1, remember a 0 by fiddling with the set and the reset inputs. Right, so the truth table that we have for combinational logic, we now call a characteristic table, because it describes not just a purely input versus output relationship, it now describes an input and an output relative to previous output relationship. So now we call it a characteristic table. And this characteristic table is exactly the one that I've just analyzed on the circuit, but just as an iteration. While set and reset is 0, Q and not Q just keeps its previous values. It just keeps on going continuously in those values. Until I have a reset, then it changes Q to 0 and not Q to 1. And until I have a set, while reset 0, then it changes Q to 1 and not Q to 0. Also, in this case, it describes the other condition where set and reset are both equal to 1. And in this textbook, some textbooks I've seen just ignores this as a don't care because it's not supposed to happen. But in this case, 1 and 1 says let's revert both of them to 0. So while this is the case, while both of those are 1, force both outputs to be equal to 0. Okay, so now this is our SR latch. Let's just analyze this real quick. So what you have is the output Q, as I've said, and this is indicated with QA. So this here is just Q, and this here is not Q, where this is Q and this is not Q. And what we have is a timing diagram showing us a few things. The first thing it shows us is we start with a reset state. While we're in this reset state, obviously QA will be equal to 0 and QB will be equal to 1 because the set is equal to 0, right? Because we're resetting it. Then at time 1, we're dropping the reset and still set is 0. So you now need to think, how does this thing operate? It operates in a way that if set and reset are both 0, as we saw here, it just maintains its values. So for the period here, QA, which is just Q, will stay 0, and QB will stay 1. Then what happens? Then set goes to 1. Now, as soon as set goes to 1 and while set is equal to 1, the Q will change to 1 because we're setting it, and the inverse will go to 0. Then set goes back to 0. So you can see the input conditions change. Because set and reset are both 0, Q just maintains its value. It just sticks to high and not Q sticks to low. Then we have, at time equal to 4, we have a reset again. Because we have a reset and set is still equal to 0, and while that reset is in play, the Q will just be equal to 0. It forces Q to go to 0. There you go, and not Q goes to 1. Then, at time equal to 5, we go into this horrible condition. We go into this bad state, bad place, bad state. And as you can see, because R is equal to 1 and set is equal to 1, it's not a good condition, but while that's the case, both QA and QB are both equal to 0. Then this horrible condition is changed at T6. We have set goes back to 0, and we're in a reset mode again. Because we're in a reset mode, QA is 0 and QB is equal to 1. Right, that stays the case until T7. At T7, both my inputs go low. Because they're both low, these two values just maintain what they were. So Q is equal to 0 and QB, or at least QA is equal to 0 and QB is equal to 1. And then at T8, what happens? Set goes to 1. Now, because set goes to 1, and while set is equal to 1 and reset is equal to 0, we have the output set to 1 and the inverse output equal to 0. At that point, this stays the case, but at that point of T9 now, unfortunately, we go into this bad state again. So whoever controls the inputs decided to make both equal to 1, which means both change to 0. So this is how you're supposed to analyze the circuit. So in the exam, what I'll do is I'll give you those input conditions, and you have to tell me what happens at the output. And that's obviously to see if you understand how a QR, an SR latch works. Okay, now a gated SR latch. So now we have an SR latch, but that SR latch just depends on R and S. Now we're adding a little extra something to the input. Now we're saying, rather than just listen to reset and reset, let's add an enable line. It's called clock here, and you'll see in a second why. We're working towards a D flip-flop, but this is called an enable line. And unfortunately, the name that we use for enable is spelled CLK. So this enable line basically activates the two gates. So the enable line says, if clock is equal to high, if this enable line is high, then listen to set and reset. So while clock is equal to 1, behave like an SR latch. So this clock acts like a gate. It opens up the gate to enable the SR latch. However, if clock is equal to 0, then ignore reset and set, because these AND gates will just block whatever happens on set and reset. And this is described in the characteristic table. While clock is 0, then we don't care what happens to S and R. They just stay as they are. If clock is equal to 1, then we have the normal characteristic table that says either do nothing, or reset, or set, or go into this horrible mode, and this time they say don't care. Okay, how do we represent this? This is what it looks like. So we have an S, an R, and a clock enable. It's an enable that we call clock, just because we're working towards clock. And then a Q and a not Q. This is what it looks like. All right, so it's a gated SR latch, and the clock provides that gate. The enable provides that gate. Now we get to the next device. So the next device is a D latch. So now we're getting close. Now this D latch overcomes the previous problem. It overcomes this condition. It says, hey, we don't want the condition where set and reset are different at different stages. So let's just combine the two and make them inverses. So instead of having a reset and a set, we now have a singular D. And this D goes into the set. It's again enabled by CLK enable. So this D enables the set, and not D drives the reset. What is the net impact of doing that? It means that if D is equal to 0, it will reset the latch. If D is equal to 1, it will set the latch, which means it's either going to make it 1 or 0, depending on what the value of D is. So if D is 0, then my output Q will just be equal to 0. If D is 1, the output key will be equal to 1. That is, if clock is also equal to 1. So, just going to rephrase this. While clock is 1, this Q will just follow D. That's all it does. While clock is 1, Q follows D. As soon as clock goes to 0, as soon as it's 0 and while it's 0, while clock is 0, D does not have any impact on Q. So Q turns into this single bit piece of memory that stores the value of D. It basically makes, it presents D's value at Q for the whole time while clock is equal to 1. And then as soon as clock goes to 0, it says, I'll remember D for you. Now, while clock goes to 0, we say that the latch is opaque. That means it doesn't do anything in terms of changing Q as D changes. However, while clock is 1, we call it transparent, because from the outside looking in, you basically see D's value on Q. So the latch is transparent while clock is 1. That becomes important in a second, so just keep that in mind. Oh, sorry, the symbol. The symbol just looks like this. So we have a clock, which is enable. It's quite important at this point to just say, note, there's no funnies here. It's just a label. Same here, just a label. Okay, soon we'll be introducing a little triangle, which means something different. But in these cases, it's level sensitive. It's just a label. All right, so now we get to just how to make this circuit. And in this circuit, we have essentially an SR latch, but then what we add is the clock signal that uses the two AND gates. So the clock enables the two AND gates, and then, as I said, the D just goes in. And while clock is 1, Q is equal to D, and while clock is, sorry, this should, while clock is 1, Q is equal to D. And this is what it looks like. And then this S is equal to R condition never occurs. Okay, what does the timing diagram look like? You should understand now that the main thing we want to test here is that you realize that it follows the level of D whenever the level of clock is 1. Q follows D when clock is 1. So let's just look at this. We have some random clock input. You don't know where that comes from. Somebody controls it. And then what you can see is D changes. Now, to start off with, Q is given as 0. And then what you should ask yourself if you analyze the circuit is, only when clock is equal to 1 does it follow D. So Q stays whatever it is until that point where clock goes to 1. Then suddenly it latches onto D and it follows D. So you can see up to this point. Now because clock changed here to 0, it means immediately D stops following Q. Q stops following D. So Q will just follow itself while clock is equal to 0. So even though D changed here, Q ignores it because it is opaque at that point. It doesn't listen to it at that point. It's only when clock goes to 1 again does Q suddenly latch onto the value of D. And for that whole period, while clock is 1, does Q follow D. Then clock goes to 0, so Q just follows itself up to the point where clock goes to 1 again. So even though D changed, Q says, I don't know about it because my enable has been set to 0. Then what happens is at this point, clock is 1. So again, at this point, Q latches onto D. It grabs D's value and keeps it, follows it, I should say, and it follows it. And while clock is equal to 1, we have a change in D. And because we have this change in D while clock is 1, it's transparent to Q, which means Q also follows that train trajectory. Over here, clock is equal to 0, so even though there's a blip on D, Q says, I know nothing. And then over here, we have the same thing. So the clock is high, you can see D changes, and at the same time Q changes as well. So this is again what you should be able to do in the exam. I'll give you this and I'll ask you to do this, or I'll give you this and then ask you, what did that look like? Not that you can do it 100% certain, but it should be possible to at least take a guess. All right, so what we've done up to now, we're very close to defining a D flip-flop now, but what we've done up to now is we've defined an SR latch. The SR latch is level sensitive, so when set and reset is at a level 1, either one of them, this will go to a 0 or a 1. We've done a gated latch. The gated latch says, while clock is equal to 1, behave like an SR latch. While clock is equal to 0, just keep your value. The gated value, or the gated latch, is very similar, except now we only have one input. We have D. D replaces Q and R, and this says, while clock is equal to 1, make Q follow D. While, I use the word while explicitly and follow explicitly. So whatever D does, do that on Q while clock is equal to 1. And that's it. So now we get to the D flip-flop. So this is the most important one. The D flip-flop is very similar to a D latch, except the big difference is now, instead of following while clock is high, it says when there's a transition in clock, take a sample, so snapshot, and keep it until you have another transition. Now you have two types. You have one that snapshots on a rising edge of clock. That is called a positive edge triggered flip-flop. That's the most common one. You also have a negative edge triggered flip-flop, which says only when there's a falling edge in clock do you take a snapshot, do you take a sample and maintain that value. So instead of being level sensitive, these are called edge triggered or edge sensitive devices. So as you can see, this is the one that's positive triggers. So it copies this, take a snapshot of it, and plonks it onto Q and keeps it there as there is an edge on clock that goes from low to high. So on a rising edge of clock, take a sample, plonk it onto Q, keep it there until you have another rising edge on clock. If you have a negative edge triggered flip-flop, it does the opposite. It says whenever you have a falling edge, take a snapshot of Q, copy it, and paste it onto Q and keep Q at that level until you have another falling edge, and then do the same. So these flip-flops are pretty powerful, and they are basically, as I said, edge controlled, and then the triangle that I have here, that denotes that it's edge triggered and not level triggered, and the bubble just denotes that it's a negative edge or a falling edge, and the normal one is just a rising edge. So how do you make these things? Well, it's very easy actually. You just use two back-to-back D latches to do so. So as you can see here, we have a positive edge flip-flop, and this flip-flop is made using one D latch called the master. I'm pretty sure that's not PC anymore. And we have another flip-flop here called the slave. And the way that this works is this N1 will continuously follow D while this clock level here is equal to high. In other words, while this clock level is low. And this continuous following will then stop as soon as this clock goes from low to high. So as soon as this goes to high, this will go to 0. So this will stop following. But then at that point, this value will, or this Q will start following this value. So we have this effect where the one follows all the time, the master follows high time, the master follows all the time, and then there's this change from a low to a high level on clock, and immediately then the slave takes over, and it then follows whatever this value here was on Q. We'll go through another analysis in a second. I just want to explain the principle. So this one is active while clock is low. This one is active while clock is high. And obviously this cannot change during either of those stages. This follows this, and the process is while clock is low, this follows, and then as clock goes high, this stops following, but that then follows here. So we have this effect that is the transition that enables this latching through event here. Again, this is a positive edge-triggered flip-flop. This is the easy way to write it, or the shorthand method of doing it. It's the condensed symbol. It's just an input and output and a clock trigger that triggers it. And let's do an analysis actually of that. So on the previous slide, as I said, when clock is 0, the master latch is transparent and the slave is opaque. So while clock is 0, this one is transparent, it follows, and this one just maintains whatever its value was. Then when clock is equal to 1, it switches over. So when clock is equal to 1, this one stops following, and then this one follows. So the net effect of that, as I said, is that the rising edge triggers the sample and hold. Let's just look at another example here. This is from another textbook. This is the negative edge triggered version of the previous one. So in this case, we have the clock coming into the master directly, and then we have the inverter, which drives the opposite side or the inverted side of the clock. So while clock is equal to 1, this will follow, and then while clock is equal to 0, this will follow that. So let's just follow the logic. Clock goes from 0 to 1 here, and then while clock is 1, as you can see, the QM is our intermediate signal. QM follows D. So while clock is equal to 1, QM does whatever D does. All right, then clock goes to 0, and when this clock goes to 0, QM stops following D because this enable is now 0. But when clock is 0, this QS will start following QM. So as you can see, when this goes to 0 and while this is 0, QS, which is the output, goes to whatever QM's value was. So D goes on to QM while clock is 1 in this region here. I'm just going to redraw that. While clock is 1, D follows, at least QM follows D, and then as soon as clock goes 0, Q follows QM. In that process, we have this double latching effect where this dropping of the clock, this edge, has caused Q's value to become equal to whatever D's value was a few nanoseconds earlier. So it latches it through. Let's just follow this a bit further. So while clock is 0, nothing changes, so nothing can come in because this is disabled. But then as soon as clock is 1 again, takes this value and plonks it into QM. So whatever D is, you can see D is 0, QM changes to 0. And this is the case all the way up to where clock is not 1 anymore. However, for this whole period where clock was 1, this is disabled and Q just kept its value. So Q just kept its cool all the way through the place where clock was equal to 1. So when clock, so while clock is 1, as I just said, while clock is 1, QM follows D, and then as soon as it goes to 0, what happens is QM stops following D. So QM says, sorry, I'm not following anymore, I'm just following myself. QM maintains its value, and at that same point, Q says, okay, I'm following QM. So because QM stays stable, Q just follows that little QM, and essentially what has happened is this falling edge has sampled D and put it onto Q, but it's done it in 2 stages. The first stage was following D onto QM and then taking QM and putting it onto Q. Okay, so this is a negative edge triggered flip-flop. Now the only add-on that we put on top of this is to put an enabled flip-flop onto it. So we add an enable line to it, and all that we do to do that is while the enable is true, the flip-flop looks like a flip-flop. While the enable is false, it ignores whatever happens on D. And there's 2 ways to do this. The one is just to use a multiplexer. So you have the clock edges here, but if enable is 0, it'll just relatch Q back into itself. So it'll just maintain Q. And then only when enable is 1 will it actually take D and latch it through onto Q. That's the one example. The other example of how to implement this, so this is just one implementation. The other implementation is a very simple just clock enable again. So clock only has an effect when enable is active. So this enable enables data through. That's one way to do it. The other way to do it is to say this enable will only enable clock to go through. Different ways to do it. And typically when you make big designs, you don't want AND gates in the path of your clock because it could cause delays. So typically you would rather choose this option. And then the symbol for this one is just like the previous slide. As you can see, this one here, it's the same. It's just now it has the enable line added to it. Okay, and then the only other thing that is really important to know is you can also reset these flip-flops. So you can also add a reset pin, and the reset can either be, this is really so important to understand, so just bear with me one more minute. The reset can either be asynchronous or synchronous, which means we add one line here and then we say choose either D, or if we have set reset equal to 1, this will turn into a 0 because the inverse of 1 is 0, which means this gate output will be 0, so it'll clock through a 0. So when there's a clock edge, it'll sample through a 0 if reset is equal to 1, which means we have built in a reset functionality. But this reset functionality is synchronous, meaning it's synchronized to the clock, meaning it waits for the clock before it does anything. It obviously tries to reset, so you put on a reset and the value here becomes 0, but the effect of it is only passed through on a clock edge. This is a synchronized reset. You can also have asynchronous resets, and asynchronous resets reset the flip-flop immediately. It clears it immediately as soon as the input goes to 0. So there's no example of how to do that, but that is the one that you typically get. And on the next slide, you can see here we have that an asynchronous preset and clear. So typically on the previous slide here we said let's make the reset 1 resets it, but typically when you buy a flip-flop, the preset which forces a 1 and the clear which forces a 0 are done using negative logic or inverted logic. So if you make preset 0, it'll make this output equal to 1. Sorry, if you make preset 0, it makes the output equal to 1. And if you make clear equal to 0, that bubble there says it's negative logic. If you make this equal to 0, then it'll force a 0 onto the output. So these preset and clears, as I say, I've seen them mostly being asynchronous, but you can get synchronous or asynchronous clear and resets. So just to describe the functionality again, you set the value of Q equal to 1 by making preset 0, or you can set the value of Q equal to 0 by making clear 0. For all other times, you want to keep preset equal to 1 and clear equal to 1 so that it operates as a normal flip-flop. That's quite a mouthful. So for the next lecture, we'll be looking at registers. Registers are basically just a stack of flip-flops combined into a longer string to save bytes and words. We'll look at shift registers, which is very crucial to spell accurately or to pronounce right. And then we also look at counters and synchronous logic design, which is more like a design principle. Good, thank you.